Okay, we looked at the global energy balance, incoming energy combined with albedo and the outgoing long wave, and we came up with the Earth's mean emitting temperature of 255 Kelvin, but this is at the top of the atmosphere, Earth emitting to space. Obviously, Earth has an atmosphere. Energy is then coming into the atmosphere and creating a surface temperature, which is what we care a lot about, and the atmospheric temperature, right? So what determines the surface temperature? That's the tricky part that we have to understand. So let's start with this relation between normalized energy of the black body that's emitting radiation and the wavelength at which it is emitting energy. So if we look at the sun is emitting at an average surface temperature of average outer surface temperature of 6,000 Kelvin, which gives it a maximum wavelength right in the middle of the visible spectrum of 0.6 micrometers. These are micrometers. And Earth is shifted way to the longer wavelengths of 10 to 12 micrometers because it's emitting at a very cold 255 Kelvin. It's receiving energy from the sun, getting warmed up and so on, producing clouds, other things, and emitting at 255 as we saw in the previous calculation. What is important then to figure out the surface temperature? Obviously, how the shortwave is reaching the surface or absorbed in the atmosphere, and how the surface is trying to get rid of the energy in longer wavelengths back to space. It's the balance at the top of the atmosphere that matters, right? For that, we need to look at the absorption spectrum of the various constituents of the atmosphere that we looked at in the first chapter. So we look at two absorption spectra from the ground to the top of the atmosphere, and from top of the atmosphere at about 11 kilometers to the very top of the atmosphere. So, okay, we'll see the structure of the atmosphere in the next chapter. In the meantime, here you have various gases, oxygen, ozone, water vapor, CO2, methane, N2O, and so on. And you can see that some of them appear multiple times, which means they are sensitive to radiation at multiple wavelengths. Okay, that's their absorption spectrum. So the emissions from the ground to the top of the atmosphere are all completely lost. So 100% is absorbed by oxygen and ozone at these short wavelengths. As we know, high energy UV bombards oxygen, splits into oxygen atoms, and produces ozone, and ozone then absorbs less energetic UV and so on. And good thing is that most of the UV gets completely absorbed by the atmosphere in the stratosphere, which we haven't defined, but you probably already know what that is. And it's a good thing because UV can damage the DNA and hurt us and give us skin cancer and so on. So various wavelengths here as we get towards longer wavelengths are near infrared, and so on, are absorbed by the greenhouse gases. So they are not sensitive to the incoming short wave, but they are sensitive to the outgoing long wave. Okay, you don't see N2 and O2 here much, even though you see O2 a lot. They are symmetric molecules which allow the short wave to go in and long wave to go out. Okay, but it's the triatomic molecules like CO2, H2O, N2O, CH4, and so on that are sensitive to longer wavelength energy or photons of longer wavelength. So they have a bending mode and a rotational mode and a vibrating mode, which gets excited when they get hit by photons of longer wavelengths, the energy that's trying to go out of the atmosphere. And that raises their kinetic energy, which is what we call temperature. So they emit because of that increased temperature to space, but the trick is they also emit it down to Earth because the black body emits in all directions, right? That's what determines the surface temperature and the temperature of the atmosphere. Very simple. So just stare at these for a bit. If you look at 11 kilometers and above, there are still greenhouse effects from methane, carbon monoxide, CO2, and so on. Okay, this is something important to remember. The other thing is here where there is no absorption from the surface to the top of the atmosphere. These are important. They are called atmospheric window, for example, here. Why? Because if you have a satellite up in the atmosphere and you're trying to measure something at the surface, then you're typically looking for radiances or radiation coming from the surface to the satellite. So you don't want it to be absorbed by anything. Like ocean color, for example, chlorophyll on the ground can be measured by looking at the green colors and yellow bluish colors coming from phytoplankton and plants on the ground and so on, and you want them to escape, so you want to see into that window where the surface is visible. There is something called Wien's displacement law, which basically says that the maximum wavelength at which a black body is emitting radiation and its temperature are multiplied together to be a constant. That helps us to estimate the average wavelength at which Earth emits, because we know that Sun is emitting at 0.6 micrometer maximum wavelength at a temperature of 6,000 Kelvin on average. If that multiplication is a constant, then for Earth, its maximum wavelength and its emission temperature must also be constant. So you divide it. So 255 times lambda m of the Earth is constant, which has to be same as lambda m of the Sun and maximum and temperature, average temperature of the Sun, emission temperature of the Sun. That gives us a average maximum wavelength of Earth's emission at 14 micrometers, which is long wavelength compared to Sun's short wavelengths. This is what we call short wave radiation from the Sun and long wave radiation from the Earth. Okay, that's a quick run through, and next we will apply this to the energy balance. So the greenhouse effect basically comes from the ability of certain gases, which we call greenhouse gases, to allow short wave to come in but trap the outgoing long wave and prevent it from directly escaping to space. It is allowed to go to space after changing the temperature of that particular gas, which means it traps energy because it also radiates that energy back to Earth. That's what determines the surface temperature of the Earth. Right? Very nice.